All right, man. Isotopes. Let's do isotopes and nuclear notation. Here we go. If you have your periodic table close by, we're going to need that. Erase my board and we'll start talking. Right. Isotopes. Atoms of the same element that have different amounts of neutrons. All right, let's talk. What makes each element unique? So John Dalton in 1808 said every atom of a certain type of element must be unique in some way. What we now know is that we on Earth, at least since Mendeleev, actually since a guy by the name of Henry Moseley, we differentiate between the elements based on their atomic number or number of protons. So each element has a unique number of protons, and that is called the atomic number. So if you have a periodic table out in front of you, on the periodic table that I gave you, I got one on the floor here. The atomic numbers are in the upper left-hand corner for each element. So if you look at a periodic table, what makes a carbon atom a carbon atom? Well, it's got an atomic number of 6. Each carbon atom has 6 protons. Each nitrogen atom has 7 protons. Each fluorine atom has 9 protons. Each neon atom has 10 protons. Each iron atom has 26 protons. Iron is Fe. It's got an atomic number of 26. You know, each sodium atom has got 11 protons. Okay, the atomic number tells you how many positive particles are in the nucleus. If you are a copper atom, then you have got to have 29 protons, right? Find copper. Copper's element 29 has got an atomic number 29. That literally means copper has 29 positive subatomic particles, positive protons, living in its nucleus. But what is not defined, okay, is the number of neutral particles. The number of neutral particles that are living in there with the protons can vary. And those are called isotopes. So, for example, let's talk about carbon. 99% of carbon is carbon 12. And that 12 is called the mass number. And it tells you the mass, the number of things in the nucleus. It tells you the sum of the protons and the neutrons added up. Okay, we have a word for those protons and neutrons, things in the nucleus. They're called nucleons. So nucleon is the generic word for anything that lives in the nucleus. So it applies to both protons and neutrons. Okay, 1% of carbon on this planet is carbon 13. So it's got 13 nucleons. Now these are both carbon. So let's talk about what that means. So since they're both carbon, they both have to have, find carbon on the periodic table, they both have to have 6 protons, right? Carbon, letter C, it's got an atomic number of 6. So these are both carbon. So what that means is that they have to have 1, 2, 3, 4, 5, 6 positive things living in the nucleus. Obviously, that nucleus is not drawn to scale. This carbon has also got to have 1, 2, 3, 4, 5, 6 positive things that live in the nucleus. That's what makes them both carbon atoms. Here's how they're different. Carbon-12 has 12 things in the nucleus. 6 of them are protons. So if you don't have to be a genius, right? If you got 12 things in your nucleus and 6 of them are positive, then there has to also be 6 neutral things, right? Okay, 1, 2, 3, 4, 5, and 6. You can get the number of neutrons by taking the mass number and subtracting the atomic number. That'll give you the neutrons. We're going to do that a whole bunch here when we get to isotopic or nuclear notation in just a second, but we're introducing the concept. Carbon-13, again, you don't have to be a genius. Carbon's got 6 protons. Okay, this isotope of carbon has got 13 things in the nucleus. If I do 13 minus 6, I must have 7 neutrons in my nucleus. This guy's got 1, 2, 3, 4, 5, 6, 7 neutrons in there. These two atoms are isotopes of one another. They are elements, they are atoms of the same element. They are both carbon. They have the same chemical properties. They have the same physical properties. The only difference is this atom is just a little bit heavier, right? Whatever the mass of a neutron is, that's how much heavier this one carbon is. Okay, so isotopes, atoms of the same element, same number of protons, same atomic number, differing numbers of neutrons, Now we can figure out the number of neutrons and protons and all that stuff in atoms by using something called nuclear notation. I've introduced you to hyphen notation, where we write the element's name and then we provide the mass number, okay, with a hyphen. If you were typing a paper about the, carbon-13, or there's even a third isotope of carbon that's even more rare called carbon-14. You may have heard of that because that's used in dating. So to figure out how old something is, because it's radioactive, it has a half-life of 5,730 years. So you can figure out how old an Paleolithic axe handle is, or how old some Neanderthal is by looking at how much carbon-14 is left in their bone. Anyway, I introduced you to hyphen notation. I now want to show you nuclear notation, and this is one of those things, man. I don't know what it is. I've been teaching chem for 15 years now. And this is one of those things, it just doesn't stick. It doesn't stick. It's like if you don't use it, you will lose it, and it will be gone. Luckily, this class is only 6 weeks long, so maybe you keep it in your brain, at least till this class is over. So nuclear notation. We take the element's symbol. So Cu for copper, Fe for iron, C for carbon, right? By the way, again, if it's a 2-letter symbol, that second letter has got to be lowercase. We then put the mass number at the top, left-hand corner, and we put the atomic number in the lower left-hand corner. Why did chemists set nuclear notation up like this? Again, you don't have to be a genius, okay? If the mass number is the sum of the protons and the neutrons, and the atomic number is the number of protons, well, if I put the protons plus neutrons on the top and the protons on the bottom, if I subtract the atomic number from the mass number, then I'll be left with the number of neutrons. That's why we set it up like that. Nuclear notation makes it really easy to get the number of neutrons, okay? Because if we subtract the mass number by the atomic number, the protons cancel out, and we're left with the neutrons. That's why we set it up like that. Now, we will eventually get to ions here in a moment. And for ions, we put a charge in the upper right-hand corner. This is where you'll see a +1 or a +2 or a -1 or a -2. And charge affects the electrons, which we'll get to. If you do not see anything written in the upper right-hand corner, then you can assume that the atom is electrically neutral. And if it's neutral, then the electrons have to be equal to the protons. Think about it. Protons are the positive particles. Electrons are the negative particles. If there's no charge, then the protons and electrons must be the same. So let's do an isotope. Let's do a really important isotope. Let's do uranium-235. Uranium-235 is a really important isotope because this is the fissionable form of uranium. This is the uranium that's used in power plant, non-breeder reactors. Breeder reactors use plutonium. But any nuclear power plant you would see in the United States, they do have breeder reactors in Europe, but we don't have any in the United States. They're not legal here. But any nuclear power plant that you see in the United States got uranium-235 in it. Some atomic weapons use uranium-235. The bomb that was dropped on, I believe, Hiroshima had uranium-235, and then the one that was dropped on Nagasaki actually was a plutonium weapon. And then they've tested all kinds of different crazy stuff since then. So let's talk about uranium-235. If I want to rewrite this in nuclear notation, the first thing I do is I find the symbol for uranium. Uranium is an actinide. You'll find it down at the very bottom. Okay, its symbol is a capital U. This is the mass number that's going to go on the top. And then we need to find on the periodic table that uranium, and we need to steal its atomic number. And uranium has an atomic number of 92. So that 92 is going to go here. Mass number at the top, atomic number at the bottom. And now I want to answer some questions about the uranium-235 atom, this particular isotope of uranium. So I want to know how many protons does this have, how many neutrons does it have, and how many electrons does it have. The protons is easy. The protons is the atomic number, literally 92. The neutrons, also pretty easy. You're going to take the mass number 235 and you're going to subtract the atomic number 92. And I believe it is pretty late at night, but I believe that's 143. 235 minus 92, 143. Still got it here at 7:08 p.m. 143. And then the electrons is easy as well, especially for neutral atoms. This has no charge. We did not indicate a charge. It is not an ion. Atoms with a charge are called ions. This is just a neutral atom. If it's a neutral atom, the number of protons and the number of electrons must be the same. Luckily, most of the uranium on Earth is not uranium-235. I believe uranium-235 is less than 5% abundant. It's not very abundant. And that's good because you have to extract the uranium-235, and it's very hard to isolate that specific isotope of uranium, which is awesome because we don't want any country on Earth having the atomic bomb. Like, that's probably not a good idea. Like, we want countries that would have to work for it to be able to get it, right? And it also makes it very difficult, hopefully, knock on wood, for like a terrorist organization to extract pure uranium-235, right? It's not, you need a massive plant. During the Manhattan Project, 10% of the United States electricity went to extracting uranium-235 from the ore. 10%. Just wrap your mind around that. There was a plant in Oak Ridge, Tennessee, and 10% of the United States electricity went to Oak Ridge, Tennessee during the Manhattan Project to extract pure uranium-235 from the rock. Okay, the vast majority of uranium is uranium-238. Here's what I want you to do. I want you to rewrite that in nuclear notation. And then I want you to tell me how many protons, neutrons, and electrons are in uranium-238. I want the nuclear notation. Tell me how many protons, neutrons, and electrons, and then we're going to compare the two atoms. Go ahead. All right. So uranium-238, it's still uranium. It's got an atomic number of 92. We subtract, now it's 146. Somebody tell me if I did that wrong. And then it's still neutral, so 92. How are we doing? Do you see how these are isotopes of one another? Same atom, 92 protons, different number of neutrons, 143. This guy's got 3 more. Those 3 neutrons really stabilize the atom. When you remove those 3 neutrons, this thing becomes incredibly unstable and capable of having fission happen to it, which we won't get into. But yeah, cool. Let's practice some more. Let's do it. I'll tell you what. Let me put another one up here, and we'll talk about ions, which are going to be the main topic of tonight, because we're just getting started. We're in like the bottom of the second inning, folks, of tonight. All right, let's do, oh man, I don't know. Just pick a good element here. Yeah. Let's do iron 56. I want you to rewrite that in nuclear notation. And I want the protons, the neutrons, and the electrons. Go ahead. All right, hopefully you found iron. Iron, the Latin word for iron is ferrum. That's where the Fe comes from. The 56 is the mass number, and 26, I believe, is the atomic number of iron. So the protons are 26. We subtract 30 neutrons. It's electrically neutral. Got to be 26, right? Awesome. Let's talk about ions. I'm going to leave this because we won't come back to it. I'm going to write it over here. Ion. An atom with a charge. And what does it mean to have a charge? Well, if you're not neutral, then your protons and your electrons do not match. So protons do not equal electrons. That's what it means to be an ion. And there's 2 scenarios, and there's 2 different kinds of ions. We have cations. Cations are positive ions. And let's think about, what does it mean to be positive? Well, if you're a positive ion and you have a net positive charge, you must have more protons than electrons. So the protons must be greater than the electrons if you're a positive ion, if you're a cation. Metals are like to be positive. Talk about why. The things underneath the staircase are going to be our cations. They take on a positive charge. The other kind of ion is an anion. Anions have a negative charge. They're negative ions. And think about it, how would you have a negative charge? Well, you must have more negative particles than positive particles. If you have more negative particles than positive particles, your protons are less than your electrons, or your electrons are greater than your protons, however you want to think about it. And we can now figure this out. Okay, iron, so I got the luxury of a whiteboard. It is so awesome, right? I know you guys got paper. Some of y'all got like iPads and stuff though, right? So you got that. If we put a charge on our iron atom, and iron is what's called a type 2 metal. Give me an hour, and you guys are gonna know what a type 2 metal is. Iron is a type 2 metal, and it likes to be +2 or +3. So we're just gonna pick one. We're gonna say iron 3, or the +3 charge. If that iron now has a +3 charge, that charge affects the electrons. My electrons are no longer going to be 26. So when you have an ion or a charge, that does not affect your protons. It's still iron. So it's got to have 26 protons. That's what the symbol tells me. Okay, the neutrons I get by subtracting the mass number by the atomic number. When you have a charge, it's your electrons that are impacted. And now you kind of got to think. You say, all right, if I have a net positive 3 charge, I must have 3 more positive particles than negative particles. I must have 3 more protons than electrons. There must only be 23 electrons in that atom. So that's how it works for cations. Now, maybe you're the kind of person who likes to memorize stuff, right? So, like if I got a positive ion, then I got to subtract that charge from the atomic number to get there. I don't like to memorize things. I like to think about things, right? Because that's just me. Let's do an anion. So in a cation, you have less electrons than protons. Let's do an anion. Fluoride. Most fluorine on this planet is fluorine 19. If you find fluorine on the periodic table, it's element 9. And fluorine likes to have a -1 charge. Now, if a charge is +1 or -1, you don't have to write the 1. You can, okay? So I'm going to write the 1, but you certainly don't have to. I want to know how many protons, how many neutrons, and how many electrons are in this fluoride anion. Awesome. So protons, 9, subtract 10. And now, if we look at this, it's got a -1 charge. What does that mean? That means in order to have a net -1 charge, I must have 1 more electron than proton. So if I have 9 protons, my electrons must be 10. How about I give you like a couple more? We'll practice the nuclear notation thing. You telling me how many protons, neutrons, electrons, all that stuff. We'll do average atomic mass calculations, and then we'll take our break, and then we'll come back for the second 2 hours. Anyway, stop me. I mean, obviously, y'all ever have any questions? Unmute yourself, yell out, right? Or type in the chat or something. Let me know. All right. I got 3 atoms and ions up here. I want you to tell me using your periodic table. You'll need the periodic table because I do not give you the atomic numbers. You have to find the elements. I want you to tell me how many protons, neutrons, electrons are in the sulfur atom, how many protons, neutrons, electrons are in the scandium ion, and how many protons, neutrons, electrons are in that iodide ion. Give it a shot. All right. This top guy, this sulfur atom, I got 16 protons, 21 neutrons, 16 electrons. No charge written, so the protons and the electrons must be the same. This scandium atom, 21 protons, you subtract 23 neutrons. It's got a +3 charge. It's got 3 less electrons than protons, so that's 18. And then for this iodide, you look up iodide, it's got an atomic number 53. Subtract 72 neutrons. It's got a -1 charge. It's got 1 more electron than proton, so it must be 54. How are we feeling about nuclear notation? Anybody have any questions? Give me a thumbs up. If you've done that before and you're like, oh man, that's old news and I could totally do that. Oh yeah. Ooh, and there's like a celebration symbol there. That's crazy. Awesome. Love it. Love it, love it, love it. Okay. Let's do calculating average atomic mass. And then we'll move on. We did all that stuff. All right, here we go. Average atomic mass. If you look on the periodic table, let me pull up periodic table. If you look on our periodic table, and every periodic table is a little different, but if you look at our periodic table, these numbers down at the bottom, these are our average atomic masses. Here's the problem, folks. 99% of the carbon on Earth has 12 things in its nucleus. It's got a mass of 12. And 1% of the carbon on Earth has got 13 things in the nucleus. So the problem is, if I want to refer to the mass of a carbon atom, which isotope am I talking about? Or if I have a bottle of carbon, maybe I got a bottle of graphite or a diamond, right? And I want to talk about the mass of the carbon atoms in there. Well, they're not all the same because there's different isotopes found in nature. So what chemists have decided to do was to take the percent abundance of each isotope found on Earth. Okay, don't ask me where they get those numbers. Somebody, somehow, somewhere figured out what percent of the carbon on Earth is carbon 12, what percent is carbon 13, what percent is carbon 14. I don't know how they did that, but they figured it out because there's so much carbon, you know, like in the air and the ground. And anyway, they figured out the percent abundance of each isotope for the atom, and then they essentially averaged them out. Well, how do we do that? That's our first problem here. It's very simple doing these problems. So 98, I'm just going to rewrite these numbers on the board here. 98.9% of the carbon on Earth is carbon 12, so almost 99. And 1.1% of the carbon on Earth is carbon 13. Awesome. So how do we take the percent of the carbon on Earth that's this mass and the percent of the carbon on Earth that's this mass, and how do we get an average mass out of it? It's very simple. We take the mass number for this isotope times its percent as a decimal. So you got to divide this by 100 or move that decimal point 2 places to the left, 0.989. So you need to turn it back into a decimal, get rid of the percent. We're going to divide that by 100 or move the decimal point twice, so that's 0.011. What we do is this. We take the mass, the average mass is going to be our mass number times its percent abundance as a decimal, 0.989, plus our next mass number, our next isotope, times its percent as a decimal. So let's pop that in. 12 times 0.989 plus 13 times 0.011. You don't actually need those parentheses, by the way, because order of operations is going to multiply before it adds anyway. So you don't actually need those parentheses. But, and sig figs, because percents were involved, I'm not going to nail you on sig figs. Anytime percents are involved, we don't worry about sig figs because our percent doesn't have units. It's not really a measurement, right? If you kind of think about it. So it gets super crazy. There's special rules for sig figs and percents. We ain't getting into that. Okay, but anyway, that's where the 12.01 comes from. Take a look at this. Go to your periodic table, find carbon. What's the average atomic mass of carbon? 12.01, right? That's where they got that. Now, your periodic table, they had a lot of data. So they've gone, like, they'll go out to the thousands place or whatever. I usually just round them to the hundreds place. Let's have you try the next one. Go ahead, try to give me the average atomic mass of chlorine if 75.8% of the chlorine on Earth is chlorine 35 and 24.2% of the chlorine on Earth is chlorine 37, and then check your work using the periodic table because I didn't make these numbers up. I actually looked it up. Go ahead. I got 35.48. We're not going to put any units on here. We'll actually get to the units on tomorrow. God, summer. I'm not used to it being every day yet, you know. Anyway, for now, you can write AMU for atomic mass unit. It's eventually going to be grams per mole. We'll get there. I've got one more here before we take our break. Try this one. Silicon's got 3 major isotopes. Okay, silicon 28, silicon 29, and silicon 30. Go ahead and give me the average atomic mass of silicon. I got 28.11. We just have 3 isotopes, so we do it 3 times, and there it is. Awesome.